Possible causes of transformer failure include overvoltage, overload, and the condition of the transformer. The transformer's high side is rated for 480 volts, while the incoming voltage from the phase converter is 218 volts on one leg. This could have caused insulation breakdown in the transformer, leading to a short circuit. The transformer's maximum rated current on the 240 volt side is 278 amps. The maximum draw being 62 kVA corresponds to approximately 258 amps. While this is below the rated capacity, prolonged operation at high load levels can weaken the transformer. The unit was purchased used, so it's possible that it was already nearing its end of life or had underlying issues. Heat build-up and discoloration of coils can indicate impending failure. Here is some advice for installing a new transformer. Firstly, voltage verification should be performed. Confirm that the incoming voltage from the phase converter matches the rated voltage of the transformer's high side, which is 480 volts. Secondly, consider proper sizing. Ensure that the transformer's capacity is sufficient to handle the maximum load requirement of the molding machine. Thirdly, continuous monitoring is critical. Regularly monitor the transformer's temperature and voltage to detect any potential issues early on. Fourthly, ensure proper grounding and overcurrent protection measures are in place to prevent electrical hazards. Regarding the 218 volt input, theoretically, using a voltage slightly higher than the transformer's rated voltage on the high side can cause overfluxing, leading to increased heat generation and reduced transformer life. However, in this case, the difference is relatively small, 218 volts versus 240 volts. And likely did not contribute significantly to the transformer failure. Other considerations include consulting with an electrician or transformer specialist for professional advice. Check the phase converter for any potential issues that could have contributed to the overvoltage or overload in the transformer. Finally, consider using a voltage regulator to stabilize the incoming voltage to the phase converter and transformer. To expand, transformers are designed to operate within specific voltage and current parameters. Exceeding these limits can lead to several problems, including insulation breakdown, core saturation, and overheating. Each of these issues can significantly reduce the lifespan of the transformer and, in severe cases, cause catastrophic failure. Firstly, let's delve deeper into overvoltage. When a transformer is subjected to a voltage higher than its rated value, the insulation that separates the windings can break down. This breakdown occurs because the electric field strength within the insulation material exceeds its dielectric strength. The dielectric strength is the maximum electric field that a material can withstand before it begins to conduct electricity. When the insulation fails, it creates a short circuit between the windings, leading to a significant increase in current flow. This can cause the transformer to overheat rapidly and potentially result in a fire or explosion. Secondly, overload is another common cause of transformer failure. A transformer is designed to handle a specific amount of apparent power, measured in kVA. When the load connected to the transformer exceeds its rated kVA, the transformer is said to be overloaded. This overload causes the current flowing through the windings to increase beyond the design limits. The increased current generates more heat due to the resistive losses in the windings, which are proportional to the square of the current, as described by Joule's law. If the heat generated exceeds the transformer's cooling capacity, the temperature of the windings will rise. High temperatures can degrade the insulation material, reducing its dielectric strength and increasing the risk of short circuits. In addition, prolonged operation at high temperatures can cause the transformer oil, if present, to break down, further compromising the insulation. Thirdly, the age and condition of a transformer play a crucial role in its reliability. Over time, the insulation material in a transformer can degrade due to thermal stress, moisture, and chemical contamination. This degradation reduces the insulation's ability to withstand high voltages, making the transformer more susceptible to failure. Similarly, the core of the transformer, which is made of laminated steel, can deteriorate due to corrosion and mechanical stress. This deterioration can increase the core losses, which further contributes to the transformer's overheating. Regular maintenance, including inspection, testing, and cleaning, can help to identify and address these issues before they lead to failure. Now, let's discuss the steps for installing a new transformer safely and efficiently. Firstly, voltage verification is of utmost importance. Before connecting the transformer to the power source, it is essential to verify that the incoming voltage matches the transformer's rated voltage. Using a voltmeter, measure the voltage at the transformer's terminals and compare it to the nameplate rating. If the voltage is too high or too low, it can damage the transformer. If the voltage is too high, it can cause overfluxing, which leads to increased core losses and overheating. If the voltage is too low, it can cause the transformer to operate inefficiently and potentially damage the connected equipment. Secondly, proper sizing is critical to ensure that the transformer can handle the load without being overloaded. To determine the appropriate transformer size, calculate the total kVA of all the equipment that will be connected to it. Add a safety factor of at least 25% to account for future load growth. Select a transformer with a kVA rating that is equal to or greater than the calculated value. Using a transformer that is too small will cause it to overheat and potentially fail. Thirdly, continuous monitoring is essential for detecting potential problems early on. Install temperature sensors and voltage monitors to keep track of the transformer's operating conditions. Monitor the transformer's temperature regularly and compare it to the manufacturer's recommendations. If the temperature is consistently higher than normal, it could indicate an overload, a cooling problem, or insulation degradation. Also, monitor the voltage to ensure that it remains within the acceptable range. Significant voltage fluctuations can damage the transformer and the connected equipment. Fourthly, grounding and overcurrent protection are essential safety measures that protect the transformer and the connected equipment from electrical faults. Ensure that the transformer is properly grounded to provide a low impedance path for fault currents. This grounding helps to prevent electric shock hazards and reduces the risk of equipment damage. Install overcurrent protection devices, such as circuit breakers or fuses, to protect the transformer from overloads and short circuits. These devices will automatically disconnect the transformer from the power source if the current exceeds the safe limit. The size and type of overcurrent protection device should be selected based on the transformer's kVA rating and the applicable electrical codes. Furthermore, let's consider the issue of the 218-volt input. While it is generally recommended to operate a transformer at its rated voltage, a small deviation is often acceptable. In this case, the 218-volt input is slightly lower than the transformer's rated 240 volts. This difference is unlikely to cause significant problems as long as the transformer is not overloaded. However, it is important to note that operating a transformer at a voltage significantly lower than its rated value can reduce its efficiency and potentially affect the performance of the connected equipment. For additional considerations, it is always advisable to consult with an electrician or transformer specialist for professional advice. These experts have the knowledge and experience to assess your specific situation and recommend the best course of action. They can also help you to select the appropriate transformer size, install it safely, and maintain it properly. In addition, it is important to check the phase converter for any potential issues that could have contributed to the overvoltage or overload on the transformer. A malfunctioning phase converter can produce unstable voltage and current, which can damage the transformer. Have the phase converter inspected and repaired if necessary. Finally, consider using a voltage regulator to stabilize the incoming voltage to the phase converter and transformer. A voltage regulator can help to maintain a constant voltage even when the incoming voltage fluctuates. This can protect the transformer from overvoltage and undervoltage conditions, extending its lifespan and improving its reliability. When dealing with electrical equipment like transformers, safety should always be the top priority. Always follow the manufacturer's instructions and the applicable electrical codes. If you are not comfortable working with electricity, hire a qualified electrician to do the job. Remember, working with electricity can be dangerous, and improper handling can result in serious injury or death. Furthermore, transformers are essential components in electrical power systems, used to step up or step down voltage levels to match the requirements of different equipment and applications. They operate based on the principle of electromagnetic induction, where a changing magnetic field in one coil induces a voltage in another coil. The efficiency and lifespan of a transformer depend on various factors, including its design, materials, operating conditions, and maintenance practices. Understanding these factors and implementing appropriate measures can help to ensure the reliable and efficient operation of transformers. Insulation breakdown is one of the most common causes of transformer failure. The insulation material, typically made of paper, varnish, or oil, provides electrical isolation between the windings and prevents short circuits. Over time, the insulation can degrade due to thermal stress, moisture, chemical contamination, and electrical stress. The degradation process can be accelerated by high temperatures, excessive voltage, and exposure to contaminants. Regular inspection and testing of the insulation can help to identify potential problems before they lead to failure. Overload is another significant factor that can contribute to transformer failure. When a transformer is overloaded, the current flowing through the windings exceeds the design limits, causing excessive heat generation. The heat can damage the insulation, reduce its dielectric strength, and ultimately lead to a short circuit. Overloading can also cause the transformer oil, if present, to break down, further compromising the insulation. To prevent overloading, it is essential to select a transformer with a kVA rating that is sufficient to handle the maximum load. Also, monitor the transformer's temperature and current regularly to detect any signs of overloading. Core saturation is another potential issue that can arise in transformers. The core of a transformer is made of laminated steel and provides a path for the magnetic flux. When the magnetic flux density in the core exceeds its saturation point, the core becomes magnetically saturated. This saturation can cause increased core losses, reduced efficiency, and distorted output voltage. Core saturation can be caused by overvoltage, excessive load, or harmonic currents. To prevent core saturation, it is important to operate the transformer within its rated voltage and current limits. Also, use filters to reduce harmonic currents in the power system. In addition to these technical factors, environmental conditions can also affect the performance and lifespan of transformers. High humidity, corrosive atmospheres, and extreme temperatures can accelerate the degradation of the transformer's components. Protect the transformer from these environmental factors by installing it in a suitable enclosure and providing adequate ventilation. Regular maintenance is crucial for ensuring the reliable and efficient operation of transformers. The maintenance program should include regular inspections, testing, cleaning, and lubrication. Inspect the transformer for any signs of damage, such as cracks, leaks, or corrosion. Test the insulation resistance, turns ratio, and winding resistance to assess the condition of the transformer. Clean the transformer to remove dust, dirt, and other contaminants that can affect its performance. Lubricate the moving parts, such as the cooling fans and tap changers, to ensure smooth operation. By implementing a comprehensive maintenance program, you can extend the lifespan of your transformers and prevent costly failures. Furthermore, consider the specific application of the transformer. For example, if the transformer is used in a critical application such as a hospital or data center, it is important to have a backup transformer available in case of failure. Also, consider using a transformer with advanced features, such as automatic voltage regulation and remote monitoring, to improve its reliability and performance. Ultimately, the best way to prevent transformer failure is to understand the factors that contribute to it and implement appropriate measures to mitigate these risks. By following the recommendations outlined in this discussion and consulting with qualified professionals, you can ensure the reliable and efficient operation of your transformers for many years to come. To be perfectly clear, the information provided here is for general guidance only and should not be considered a substitute for professional advice. Always consult with a qualified electrician or a transformer specialist before making any decisions about your electrical system. Ignoring safety precautions and industry standards can lead to dangerous situations. Electrical work should only be performed by qualified individuals who have received proper training and certification. It's also important to consult the National Electrical Code, specifically Article 450, for further guidance. Article 450 covers transformers in detail, including installation requirements, ventilation, overcurrent protection, and grounding. Familiarize yourself with the relevant sections of this article to ensure that your transformer installation complies with all applicable codes and regulations. For example, NEC Table 450.3 outlines the requirements for transformer overcurrent protection, specifying the maximum allowable size of the overcurrent device based on the transformer's kVA rating and voltage. Additionally, NEC Section 450.11 provides guidelines for transformer ventilation, ensuring that the transformer is adequately cooled to prevent overheating. Ignoring these requirements can lead to transformer failure and potentially create a fire hazard. Always follow the NEC guidelines and consult with a qualified electrician to ensure that your transformer installation is safe and compliant. Furthermore, proper grounding is essential for transformer safety. Grounding provides a low impedance path for fault currents, which helps to prevent electric shock hazards and reduce the risk of equipment damage. The NEC specifies the requirements for grounding transformers in Article 250. Ensure that your transformer is properly grounded in accordance with these requirements. Finally, remember that electricity is dangerous, and improper handling can result in serious injury or death. Always take the necessary precautions and consult with a qualified electrician before working with electrical equipment. Remember to consult a qualified electrician for assistance. The voltage should be checked with a calibrated meter to ensure the accuracy of the reading.